Welcome to another exciting pre-calculus video. In this one, we're going to start looking at the last section in this chapter, 4.7, inverse trigonometric functions. And the bullet points are, we're going to evaluate and graph inverse sine. That'll be this video. In the next one, we'll look at evaluate and graph other inverse trig functions. And finally, evaluate compositions with inverse trig functions. That will be the day 3 video. But before we get into this inverse stuff, let me back up here. Let's do some refreshers. Here is just a warm-up question on the unit circle. This is what we've seen before. We're asked to find the sine or the cos or sometimes the tan of some angle. So imagine this problem starts at the center of the circle. I'm here at this blue dot, and I see here the sine of pi over 3. So I find the pi over 3 ray that leads me out of the center of the circle. So here's pi over 3, and that leads me to this point on the edge of the circle. And since I want the sine, I'm going to look at the y-coordinate. So the sine of pi over 3 is root 3 over 2. Now the sign here, next one, negative quarter pi. So we're going to go in the clockwise direction. Here's 0. And we're going to go 1/4 pi in the clockwise direction. So that's going to take us here to this ray, leads us out to the end of the circle. And here is the point. The sine value again is the y-coordinate. So that will be a negative root 2 over 2. So here again, these type of problems, you're sort of starting at the center of the circle, and then you follow an angle out to the edge, and once you're on the edge, you find the value in the x or the y coordinate. Now this section's about inverses, and this sine here does have an inverse function, and one of the ways to denote it is sine inverse. You know, we got this sort of negative 1 exponent. Negative exponents usually mean you're going to move that to the denominator. So here a little bit of confusion. Sine inverse is not the same thing as 1 over sine. 1 over sine, that's cosecant. You know, sine and cosecant are reciprocals. Sine inverse is a little bit different. So this sine to the negative 1 power just means the inverse of sine, not the reciprocal. Here in the sine function, angles go in, values come out. So here it says any angle goes in, the sine of some angle. We can put any number in for x. The numbers that pop out are going to be a number between 1 and negative 1. Now, for sine inverse, those domains and ranges will flip. So for sine inverse, the only thing that's allowed to go in here are numbers between 1 and negative 1. And then what's going to pop out is some angle. And we're going to see shortly that those angles will be from negative half pi to positive half pi. And you'll see why shortly. So again, the original sine, angles go in, numbers between negative 1 and 1 come out. In the inverse, numbers between negative 1 and 1 go in, and out pops some angle. So here we go. First, I got a little graph drawn there, sine wave. Is sine a function? And if it is, how would you know? So we have a vertical line test. Here's a vertical line. And if I move it across the graph of the sine wave, it only hits at one spot at a time. So it is a function. Does sine have an inverse? Well, then we'd need to do the horizontal line test like this. So if I put a horizontal line over it, we run into trouble very, very quickly. My line's not very horizontal, but we see we're going to hit here in 1, 2, 3, 4 different spots. And remember, the sine wave goes on infinitely, so we're going to be hitting a lot of spots on the curve. So does sine have an inverse? Well, in this case, no, it doesn't. But we can restrict the domain and make it have an inverse. And here's how the book explains it. Let me make this a little bit bigger. Recall back in section 2.7, for a function to have an inverse, it must be 1 to 1. That is past the horizontal line test. We can see that the sine function does not pass the test because different x values yield the same y value. However, if we restrict the domain from negative to positive half pi, corresponding to the darker portion of the graph above, the following principles will hold. On that restricted interval, the function is increasing. On that restricted interval, y equals sine x takes on its full range of values, every number from -1 to +1. On that restricted interval, y equals sine x is 1 to 1, or again, it will pass the horizontal line test. So again, here in the picture, the light gray is the sine wave, and again, it would fail the horizontal line test unless we chop it off, unless we restrict it. So here, this darkened portion of the graph goes from the x value of -0.5 pi to +0.5 pi. At -0.5 pi, we're down in the bottom of a valley. By the time we get to +0.5 pi, we've reached a peak, so we have achieved every value in between. So on that restricted domain, y equals sine x has a unique inverse function called the inverse sine. It is denoted two different ways. The one on the right, we already saw this. Y equals sine inverse of x. And also we could put the word arc in front of it. The inverse of sine is the arc sine. So these are interchangeable. The book does bounce back and forth pretty frequently. So those are exactly the same thing. And over here, I just drew a little picture of the xy axis. Remember now here, sine inverse, when we're working with sine inverse, we have to stay between -0.5 pi and +0.5 pi. On the coordinate axis, it looks like this. From the positive x-axis counterclockwise takes us to +0.5 pi. If we go clockwise, that'll take us to the -0.5 pi. So this notation, sine inverse x, is consistent with the inverse function notation f inverse of x. The arcsine x notation, which is read as, quote, the arcsine of x, comes from the association of a central angle with the intercepted arc length on the edge of the unit circle. So arcsine x means the angle, or the arc, whose sine value is x. Both notations, arcsine and sine inverse, are commonly used in math, so remember that sine inverse x denotes the inverse sine function rather than 1 over sine. The values of arcsine x lie in the interval positive to -0.5 pi. The graph of arcsine is shown in example 2. So here in the box we have our official definition of inverse sine. There we go. The inverse sine function is defined by y is equal to the arcsine of x if and only if the sine of y is equal to x. Now let me show you how they went from one to the other. Here in red ink, I'm underlining y equals arcsine x. If we want to do something to one side, we have to do it to both sides to be fair. So let's say I wanted to take the sine of the left side, so this becomes the sine of y, and then I'm going to take the sine of the arcsine. Sines and arcsines are inverses, so these will cancel each other out. So what we're left with over here is just the x. X is equal to the sine of y, and that's exactly up here. I'm underlining in blue. So y equals arcsine x if and only if the sine of y is equal to x. X must be a number between 1 and -1. Y must be an angle between positive and -0.5 pi. The domain of y equals arcsine is -1 to 1. The range is positive to -0.5 pi. Let me even do this. You've seen this before in pre-calc. X squared and the square root of x. They are also inverses. If I take x squared and I square root it, the square and the square root cancel, and it's just equal to x. If I take the square root of x and square that, the square and the square root cancel, and we're just equal to x. So it doesn't matter what order we go in, the root of the square or the square of the root, the answer is the same either way, just x. You're going to see that also with sine and sine inverse. If I have the sine inverse of angle x, and I take the sine of that, the sine and the sine inverse will cancel, just leaving the x. Okay, example 1. If possible, find the exact value. And we're going to need a unit circle. Bam, there it is. So now I got the full unit circle here. Remember arc sine. If you're trying to answer an arc sine question, we can only go from 0 to positive a half pi and 0 to negative a half pi. So for arc sine, we want to stay in this neighborhood. You know, we don't want to wander too far out of our neighborhood. Somebody might mug us and steal our calculator. So we want to stay here in this neighborhood for arc sine. So here we want the arc sine of negative a half. Remember that sines are associated with y coordinates. So let's start looking for a y coordinate of negative a half. y1 root 3 over 2. So we're working our way down. Here it is. Negative a half is on this point, and if I find the angle that made it happen, you might think the answer is 11 pi over 6. But remember, we don't want to go out here through the bad neighborhoods to get to that angle. So 11 pi over 6 is going to get marked wrong. We need to get there quicker, a shorter, straighter way to get from 0 to 11 pi over 6. So we're going to take the negative root. That's going to be negative pi over 6. Up next. Now notice here they went from arc sine to sine inverse. You know, it's the same question. These are interchangeable. So we want to find a y coordinate of positive root 3 over 2. So now we're definitely going to be in quadrant 1. Here is our y coordinate of root 3 over 2. What angle made it happen? Pi over 3. So the sine inverse of root 3 over 2 is pi over 3. Last one, C, sine inverse of 2. If we start going around the unit circle looking for a y coordinate of 2, we're never going to find it. Because remember, up here at the top, this is as high as we ever go on the y-axis. We only go up to a height of 1. So here, they're trying to find a spot that's a height of 2. That is not on the unit circle. If you punch that in a calculator 2 and hit sine inverse, it's going to say error. Or we could use undefined. You know, sine inverse is not defined at 2, or 2 is outside of the domain of sine inverse. Remember, we can only put numbers in there between 1 and negative 1. We try to put in a 2, an error message is going to pop out of there. Okay, remember, stay in the good neighborhoods, quadrant 1 and quadrant 4 for arc sine. Example 2, they do say here we're going to sketch a graph of this inverse function, the arc sine x. And here we've got a table. And I'm not even going to read this. Let's just fill in some of the stuff of the table. So remember, now we're dealing here with sine values. So where is sine equal to negative 1? Well, that'd be negative pi over 2. Next, negative root of 2 over 2. If we look on our unit circle, that's going to be down in the fourth quadrant. That is going to be, yeah, that is a negative there. It sort of bled in. A negative pi over 4. Negative a half as a sine value would come from negative pi over 6. The sine of 0 is 0, so the sine inverse of 0 will also be 0. And now we're up into quadrant 1. If you look at the y-coordinates, 1/2 comes from pi over 6. Root 2 over 2 comes from pi over 4. And positive 1 is top of the circle. Up at the top of the circle, we're at pi over 2 as our x, or our the angle that makes it happen. Okay, now to come up with a graph of this, we could just plot those points. Let me make this a little bit bigger. There we go. So here, this would be 1 comma pi over 2. So the x is the value, and in the y spot is the angle that made it happen. Here's our root 2 over 2. That'd be pi over 4. 1/2 comma pi over 6. And now that we're down here, these will just be the negative reflections. Negative 1/2 is going to have an angle of negative pi over 6. Here we'll have a negative pi over 4. And then finally, at negative 1, the angle there would be negative pi over 2. And if we connect the dots, we get this curve snaking through the origin. You know, much like sine does always start at the origin unless we're shifted and run out through a cycle. Here we are also going to go through the origin on this graph. All right. Team huddle time. Try these practice problems. And then we also got 3 more for the mastery. So let me get a unit circle here. Abracadabra. There's one there. And let me move this over. So, you know, pause the video and see if you can figure these out. Remember, angles are going to be your answers that come out here. There's another unit circle. So again, pause the video and try these in your notes, and then start it up and see if you got it right. Okay, I hope you paused the video. Arc sine of 1/2. Again, we want to stay in the good neighborhoods where arc sine lives, quadrants 1 and 4. And we want a y value of 1/2, and there's a y value of 1/2. And what angle made it happen? Pi over 6. Pi over 6. Now, if we did not restrict our domain, there's also a y value of 1/2 over here, and that would be at 5 pi over 6. But if we don't restrict that domain, it's not a one-to-one function. It's going to fail the horizontal line test. Okay, up next down here, let me switch to red ink. Negative root 3 over 2, sine inverse of that. So let's go down to quad 4. Here is our y value, negative root 3 over 2. What angle made it happen? Is it 5/3 pi? Not exactly. Remember, if we go that way, boom, we go into the bad neighborhood. And you don't want to go through the bad neighborhood. Somebody's going to jump in and steal your calculator. So we want to get there quicker. If we go in the negative angle direction, it's going to be negative pi over 3. There we go. Stay out of that bad neighborhood. A few more here. Arc sine 0, sine inverse negative root 2 over 2, arc sine root 2 over 2. All right, arc sine of 0. Look for a y value. Again, we want to stay over here in the good neighborhoods. We don't want to go to the bad ones. Here our y value is 0. What angle made it happen? 0 radians. Sine inverse negative root 2 over 2. Well, we're down here in quadrant 4 where the y values are negative, and that is 7 pi over 4. But remember, we don't want to go through the bad neighborhood to get there. So we're going to go in the negative angle direction, 2 pi over 4. Negative pi over 4. Last one, arc sine root 2 over 2. It's positive. Now we're up here in quad 1. Angle that made it happen, positive pi over 4. And there we go. Now some bad news for you. There is no homework assignment to go with this section, because if you think about it, you know, here on the unit circle, we're only going to stay in the good neighborhoods. We can do the arc sine of 1 root 3 over 2, root 2 over 2 1/2, or the negative ones. Between the examples and the practice problems, we've kind of done the arc sine of everything. So sadly, there is no homework for this section. If you really want to do something, I guess you could go to Khan Academy and watch his video on this, and then write a little Rotten Tomatoes review whose video was better, Sal Khan's or mine. So no homework. I will see you in the next video where we talk about arc cos and the other ones. I hope this video helped.